Hi everyone, this is the video from Module 3 in Lesson 8, and this video will talk about optimization. So in the previous video we talked about partial derivatives, and then we've seen how to use them to find local extrema and then absolute extrema. In this video we're going to apply them to start optimizing functions. So we will talk first about how to set up an optimization problem, and then I will just run through a couple of examples. Each of the examples is going to take a little bit of time. As you remember from single variable calculus, optimization problems take a while. So I will show you some of the tips and tricks that can maybe speed up some optimization problems. First, let me go through this procedure for setting up an optimization problem. I'll mention first of all that there's always a context here, and the context, one of the contexts in this course, for example, is that we're dealing with real valued functions, functions that their output is a real number, for example, not a complex number or some other type of number. The other context that I'm going to assume that we're dealing with here is that the function that we're going to optimize, which is what we will call the objective function, is a function that we can find partial derivatives of, we can find the critical points for, is a function that we can do many of the procedures that we talked about in the previous videos. So I'm going to start off with the procedure then, with all that being said. First of all, we identify the function to be extremized. That is called our objective function. And then it's really useful to draw a diagram, especially now that we're going to be dealing with multivariable functions. If you can visualize what the function looks like, or if you can use some sort of technology to help you understand what's going on, then that is really going to pay off later. Number 3, using your objective function, other information in the problem, determine the relevant variables and include them in your diagram. Remember back in calculus, single variable calculus optimization problems that were applied, there was perhaps there was a plane that was flying northeast or something, then you had to label the displacement x. Or there was, I don't know, someone running through a few bases, then you had to label their displacement from home base z. So you want to include variables that are relevant to the optimization problem you're trying to solve. So that is going to come in some way from the objective function. If you're asked to, for example, maximize an area, then there are going to be some natural variables there of length and width. It's also going to come from other relevant information in the problem. So these might be constraints, for example, that I'll get to in a minute. The point being that once you have the variables that you've identified, include them in your diagram so you can see a little bit of what's changing. Remember that dynamics mindset we talked about at the beginning of the course. And also the mathematical form of the objective function itself. If earlier you were asked to maximize the volume, for example, and now you're talking about the volume of some rectanguloid, now you can write out an equation for that volume, where x, y, and z are the dimensions of the rectanguloid. So once you name variables, that will help you mathematize your objective function. That's certainly going to help optimize it later. Step number 4, extract from the problem any relevant constraints and express them in mathematical form. And then, if possible, incorporate them into your objective function. You've met many constraints in optimization problems before. A classic optimization problem is, maximize the area of a square subject to the perimeter equaling 5, let's say. The perimeter equaling 5 is an example of a constraint. Similar examples of constraints are going to come up in the multivariable context. We'll see that in the problems that I'll work out in a minute. Anyway, once you have those constraints, if you can incorporate them into your objective function, by that I mean use the constraint and solve for one variable and then substitute that into your objective function, that will make life a lot easier later on. Okay, next step. Number 5, determine the relevant domain of the objective function using everything you can. So if we're talking volume, then use your intuition that volume has to be a non-negative quantity, positive or 0. And really, even beyond that, think of 0 volume means that you have no volume. So if you're talking about, creating a box that has a certain number of dimensions, actually 0 should not be part of your domain or it should not be a possibility for the box because there would be no box. So use the real world context, use information from the constraints. If your constraints are of the form, for example, x plus y equals 1, well then that tells you that you are looking only at points along the line y equals 1 minus x, right? So we'll see in a minute how we incorporate those constraints. But the idea being that you really want to use a combination of information from the constraints and from the context of the problem to help you determine the domain. Once you have your domain, then you're going to have to make a couple of choices, maybe more. The first one is the easiest. If your domain is closed and bounded, then what we talked about in the previous video applies. So the extreme value theorem kicks in. Again, we're assuming that we're dealing with, if we scroll up here to the extreme value theorem, that we're dealing with functions that are continuous on this closed and bounded set. If so, then in the previous video we saw this theorem tells us there is an absolute maximum, there is an absolute minimum. So we go off and we try to find it. So in the simplest case, you'll be dealing with a domain which is closed and bounded, and then you can go off and follow the procedure that we had followed for in the previous video, for example, when we worked out this example. It may happen, though, as it happened in Calculus 1, that the domain you're trying to optimize over is not closed or not bounded, or both. So this is where you have some options. In most cases, especially in a course setting where we're kind of trying to teach you this and we're helping you learn it for the first time, when the domain is not closed and bounded, there will only end up being one critical point. So that would be very useful, because in that case, if that critical point is a local maximum, then it's an absolute maximum. So think back to your single variable knowledge about this. For example, if I said minimize y equals x squared, if I run through this procedure, I would eventually get to number 5. Number 5, I would say, what is a domain? I'm not given a domain. So the domain is all real numbers. This is definitely not a closed set. This is not a bounded set. It goes on forever. So how do I minimize this function? Well, I could go ahead and what I did back in Calculus 1, find its derivative, set it equal to 0, look for where it doesn't exist. In other words, find the critical points. And in this case, I would get x equals 0, y equals 0. Through a variety of ways, I could find, in this case, use the first derivative test, or use the second derivative test, or graph it, to see that 0, 0 is a local minimum. And because it's the only critical point, so that's this argument up here, because it's the only critical point, and it's a local minimum, then that makes it a absolute minimum. Right? So actually, I noticed a small typo that I'll fix here. If that critical point is a local minimum, then it is an absolute minimum. So I'll fix that typo. So the story carries over. And again, this is what will happen most of the time, I would say almost all of the time. Either the domain you're working on is closed and bounded, in which case you have this nice procedure we talked about in the previous video, or if it's not closed and bounded, there will end up being only one critical point. So that if you can show it's a local something, max or min, then it'll be a global version of that something, max or min. Great, so with all of those preliminaries aside, let's go off and solve some examples. So the first one I'm going to work out is a very, I wouldn't say typical in the sense that you'll see this particular problem everywhere, but typical in the sense of a first starting point for an optimization problem. This problem has a context, a real-world context, very interesting one actually, and it also has some things that actually simplify the problem and some things that kind of complicate it from the procedure we just talked about. Okay, so let's get into the problem and see what is going on here. So the prompt says, consider 3 species and suppose that some, but not all, members of these 3 species live in the same habitat. You can start drawing a diagram anytime you want. So I'm going to start now because I've gotten enough information. So I'm going to just, draw a circle and pretend that this is the habitat. And it's telling me that there are 3 species, some of which, but not all of them, live in the same habitat. So I'm going to draw a blob to just over here. Actually, that's less of a blob that I want to draw. there are 3 species, so let me just assume, and for nice pictorial reasons, that this blob is the first species, this blob is the second species, and this blob is the third species. Okay, so I'm drawing a habitat in which some of each of the species lives, but not all of the species live. So I've tried very hard to make the drawing capture as much of the information as possible without complicating the drawing. So far, so good. So now let's keep reading. Denote by X, Y, and Z the percentages of the habitat's population that come from members of species S1, S2, S3. Okay, great. So what's going on here? Some, but not all, of the members of the species live in the same habitat. So maybe for S1, maybe 80% of S1 lives outside the habitat. Maybe 20% lives inside the habitat. Could look at it that way. Or you could say, I'm going to look at the habitat. It's got a bunch of species in here. It's got these, and then it's got these. So what proportion of the entire habitat is these species, right? This little blue slice here. And what the problem is telling me now is that we're going to call that proportion as a percentage X. So I'm going to go in here and I'm going to put in those variables just so I can keep visualizing my situation. So S1, X percentage of the habitat is devoted to that species. S2, Y percentage of the habitat is S2 species. And then S3, Z percentage of the habitat's members are coming from species 3. So then we keep reading. One way to measure habitat species diversity is the Shannon Diversity Index. You may have heard of Shannon from information theory, and this is exactly the tie-in for this particular real-world example. And the diversity index is defined by h of xyz equals this sum of x times ln of x, all with negative signs in front of them. Okay, so interesting function. This is actually like a sum of entropies. If you look up Shannon entropy, or just entropy, you will see a lot of interesting connections here with physics and information theory. So what does the problem want us to do? Show that the maximum value, okay, so we want to extremize, we want an absolute max, of h occurs when all the variables are equal to 1/3, and that the actual maximum value is ln of 3. Okay, so what I'm going to do now is I've started following my procedure a little bit. I chose to just draw as the problem presented itself, and I've certainly added some variables. So I've done a little bit of it, but I'm going to scroll up to kind of remind you. We've identified the function to be maximized. It's this h of xyz function. That is our objective function. I mentioned earlier that this particular example I'm working on is in some sense simpler than others. This is one of the reasons which it is. We are given the objective function. We do not have to create it ourselves. That is a big help. So we did that, given to us. We drew a diagram. We looked at the relevant variables. Effectively, those were given to us. And then now we're here. So we want to extract the domain, any constraints, and then go to the domain. And then we'll check what type of domain it is. So constraints. Here's where we go back to the prompt of the problem and we go hunting. We aren't given the constraints, but we are given a lot of information. So x, y, and z are percentages of the habitat's population. So I'm just going to assume that x, y, and z are written in decimal form, like 50% is 0.5. If that's true, then x plus y plus z has to be 1. All these percentages have to be 1. So that is a constraint. Reading through the rest of the problem, I don't see any other constraints. So we are done with number 4. And then number 5, determine the relevant domain of the function using any constraints. Okay. I skipped this last little step, which I'm actually going to do, and listen to my own summary here, procedure. I'm actually going to take these constraints and substitute it into the function to simplify the function. So the way I do that is I'm going to solve here for z, 1 minus x minus y, substitute it in to h, And everywhere, therefore, I see a z, I'm going to replace it with 1 minus x minus y. And then this will be the natural log of 1 minus x minus y. Okay, so I have substituted the constraint into my objective function, producing a new objective function. So I'll go back here. Great, did that. And then now I want to determine the domain. So now we step back and we look at the function that we have, and we try to figure out what is the set of possible x, y values in this case that I can put in here that will leave the function defined. We are dealing with, oh, I noticed that I forgot the x over here, so I'll just slide that in there. Okay, and also I put a z here, that should be a y. Okay, so we are dealing with natural logs, and you may remember that natural logs domain has to be positive numbers. We can't find the natural log of a negative number. We also can't find the natural log of 0. ln of x has this vertical asymptote. The graph looks like this. Y equals ln of x has this vertical asymptote as we go toward x equals 0 from the right. It just plummets to negative infinity. So we're going to use that information here to help us figure out the domain. We also are going to use the fact that the constraint gives us some constraints on that domain. So what do we do then with all that information? First of all, here's an x, here's a y. Because of the domains of natural log, we need x and y to be positive. And then over here is another thing that we're putting into a natural log. So we need this to be positive. So if I move over the x, move over the y, or actually let me just move over the y, make it a little easier, I will get y less than 1 minus x. So I have 3 pieces of information here that literally constrain the x and y values I can look at. So I'm going to go to the xy plane. So if I look at y equals 1 minus x, that is this line here. And what I am seeing here is that the y values, as far as this problem is concerned, have to be less than 1 minus x. So they have to be below this line down here. They can't even be on the line. So to remind myself of that, I'm going to redraw this line as a dashed line, meaning I can't be on this line. So I need to be below it. But also I have to be above the x-axis and to the right of the y-axis. So basically this is my domain, this set here, the interior of this right triangle. So not including this base, not including this height, and not including that line. So that's my domain. Great, so I figured out my domain, so that is number 5. And then now we check. Is our domain closed and bounded? Well, so let's go back here. It's definitely bounded, right? It can be, remember the definition, it can be enclosed in a large enough disk around the origin. There's an example. So it is bounded. It's not closed, however, because there are clear boundaries all over the place that we are not including in the set. So I will say bounded, yes, but closed, no. So that means that I can't go back and use the simplest procedure that I could hopefully have used, which is what we talked about in the previous video. It only applies excuse me, for finding absolute extrema on a closed and bounded set. So our set is bounded but not closed. So then I'm over here. So I've kind of checked number 6. I'm at number 7. I am going to hope that our function has only one critical point, and then follow the rest of this. That will turn out to be the case, luckily. So I'm now at step number 7, and I'm going to go off and start finding the critical points. To do that, the first thing I will do is I will need the derivatives, partial derivatives of h. So I'm going to remove some of this clutter here so we can calculate some of these partial derivatives. So I'm going to go, I'm looking up here to the function itself and find h sub x, partial with respect to x. So here I'm going to have to do a product rule. Derivative of the first, derivative of x is 1, times the second, plus the first times the derivative of the second. Remember the derivative of ln of x is 1 over x. This up here is a function of y. Partial with respect to x is 0. And then over here, similar thing, I'm going to have to do a product rule. The derivative of the first with respect to x is -1, because I'm differentiating negative x. So -1 times the second function. So I'm using here the product rule. Plus the first times the derivative of this with respect to x. So that's a chain rule. 1 over that times the derivative with respect to x of that denominator. Okay, so let me clean things up here. I get minus ln of x. -1, I'm canceling here because x is not 0. Remember, that's part of our domain. I erased it, but we are not including x equals 0. ln of x is not defined there. So I cancel those two and I get -1. And then over here, I get minus ln of 1 minus x minus y. These cancel for much the same reason. We are excluding the entire set of points where this equals 0, right? That is the dashed line over here, y equals 1 minus x. We're excluding that from our domain. So we know, for example, that for sure that for our purposes, these two things are not 0, they cancel. So I just get -1. Okay, so that actually simplifies quite nicely. So what is left? First of all, I'll just multiply out the -1 to make it a little easier to see. So I'm distributing this negative, and then I'm distributing that negative. I get a +1. So I am left with +1, -1 cancels, and I get negative ln of x plus ln of 1 minus x minus y. So that ends up being fairly nice, given where we started. Now I'm just going to write down what h sub y is, and I will explain why we can just kind of jump this step. We could run through exactly all these calculations to do it all over again. However, if you go back to the function itself, there is a lot of symmetry here. So all the x's here are together, all the y's here are together, and they have the exact same form. Variable times ln of the variable, both of them with a negative sign in front. And then over here, the way that x and y appear, they appear in exactly the same way, and they're separated. They're not multiplying each other, they're not dividing each other. For all of those reasons, we can basically go back to this calculation and replace all the x's we see everywhere with the y's, swap x and y, and it will yield our partial derivative down here. So again, you can check this partial if you want to do this the way we just did, h sub x, and you will end up getting that same expression. So we now have hx and hy. We look for critical points. There are many, many places where this function, these partial derivatives are undefined. X equals 0 is one of them, y equals 0 is one of them, and then the infinite number of points where y equals 1 minus x. At all those points, the partial derivatives are undefined. However, all of those points are excluded from our domain. So on the domain we're considering, the partial derivatives are never undefined. Now let's look at where partial derivatives are equal to 0, the stationary points we've been talking about. To do that, we set these equal to 0. Okay. This first equation up here, if I move over the minus ln of x, generates ln of x equals ln of 1 minus x minus y. The second equation, if I move over the ln of y, generates ln of y equals this one. Awesome. So I could do lots of exponentiation, fanciness here, but I'm just going to note that these two right-hand sides are the same. So this implies ln of x equals ln of y. That just gets us to our next step a little faster. If I exponentiate both sides now, I get x equals y. So that is really nice, right? This problem is simplifying so nicely. So now I know that the critical point that I'm finding, the stationary point, has the property that the x and y values are the same. I can now use this and go back to any one of these relations, substitute it in, and get, hopefully, information about the numerical values of x and y. I'm going to stick with y equals x, and then substitute it in here. So I get ln of x equals ln of 1 minus 2x. And now I'm back to solving this in the sort of pre-calculus manner. I'm going to exponentiate both sides. I get x equals 1 minus 2x. And this is a nice simple linear equation to solve. So I get 3x equals 1, and I get x equals 1/3. So there begins to appear the 1/3, if I scroll up here, that we were told about in the problem. So we know we're heading in the right direction, so that's great. I have found x equals 1/3. I know that y equals x. So I also know, therefore, that y is 1/3. Great. And then I go back to my constraints way back in the beginning of the problem that we had figured out. They must, x, y, and z, all add up to 1. If I know that x and y are 1/3, then here I get 2/3. 1 minus 2/3 is 1/3. So again, I get back to the point where the problem wants me to get to. Now, all I've done so far is find out. So I'm going to write the conclusion here. Therefore, 1/3, 1/3, 1/3 is a stationary point of the function h of x, y, z. That's all I've done. So I have not yet shown what was asked to be shown, which is that h has a absolute maximum at this particular stationary point. And I certainly haven't found the absolute maximum value. But I'm very close, because if I scroll back to my procedure, I have now found the critical point. It only has one critical point. There are no other critical points on the domain. And now all I have to do is confirm that that critical point is a local, in our case, we want maximum, because then that will give us the absolute maximum that we are after. At this point, there are various ways to show that this, to show that any single critical point is a local maximum or not. Certainly, so some options. We could use the second derivative test. We talked about that in this lesson. We could do that. That it will involve calculating a few more partial derivatives and calculating that discriminant and then checking the test. Another option is we could look at a graph of the function. Could do that as well, and we'll do that in a minute. A third option is that we could look at, again, examine the domain. So we could also try that. I'm going to do this one and this one to avoid calculating some more ugly partial derivatives. So let's talk about this one for a minute. If I go back to the domain here, right, the edges of the domain, you know, I now know that in the interior of the domain, there's only one critical point, the one that we found. So you might worry, as we should, given the procedure for optimizing on a closed and bounded set, you might worry about what the function is doing at the boundary of the domain. So we can go off and try to investigate that. So what we would do then is we would look at the function, and we would, you know, pseudo take limits. I don't want to go too much in depth to this, because we are not really going to be needing this level of detail for this aspect of optimization, but I want to mention it anyway. So for example, if we are looking at y equals 0, which is this boundary, it is not included in our domain because, again, ln of y is not defined, but we could investigate the function as y approaches 0. And what would happen? Well, x would be okay as long as x is not over here at the origin. This term, if y approaches 0, might be okay. You just get 1 minus x times ln of 1 minus x. This is a term that needs some investigation. And one can show, using L'Hopital's rule, that the limit as y goes to 0 from the right, because again, natural log is not defined for negative numbers, of y times ln of y is 0. So you could do this with L'Hopital's rule. It's an indeterminate limit. You can convert it to infinity over infinity, differentiate numerator, differentiate denominator, retake the limit, you get 0. You can also show the same thing, because it's, you know, just literally replacing the letter y with the letter x, that the same thing happens for the x goes to 0 from the right. So this should tell you that on the boundary here, the value of the function is actually not going to some infinity or not, undefined. The function is actually tending to 0. Now, I haven't said anything about this part, and I will in a minute. But the point is that we're now examining the boundary, and we're getting some sense that, okay, the values are getting closer to 0. In a minute, we will calculate the h value for this, and we'll see that it's positive. So already we're getting some sense that maybe we don't need the second derivative test. Maybe because we're getting a positive value at the critical points, that might actually be the absolute maximum relative to all the points in the interior of the domain and the boundary. So now let's talk a little bit about this function. This one is kind of the same thing. Here's a little bit of a sort of trick, but it's not really a trick. It's just thinking about things differently. Again, the structure of this function is something times ln of something. And that something happens to be 1 minus x minus y. It is this line over here. If we think of that as some number like, I don't know, 2, then really it'd be like y equals 1 minus x minus 2. Right? In other words, we're changing the y-intercept, if you will, of this line. So we're maybe considering a line here or a line there. As we change that y-intercept and we make that y-intercept closer to 0, we get closer to this line. So this is a way of thinking about how you would approach this line without having to do too much work. And you could call all of this z, and therefore you could look at the limit as z approaches 0. At this point, you're still taking the limit as z approaches 0 from the right. So we don't want to insert values here that are negative because of the ln domain. But you can see that all we're doing here, this is the reason why I chose to explain it this way, is we're just changing the letters. So we're going to get the same thing, which is 0. So this is another way to convince you of this fact that you will see in a minute when I show you the graph of this function, that the z values of this function along the domain tend to 0, even though there are a bunch of ln's floating around that, as you reach these values in the domain, tend to negative infinity. But really what saves the day is that they're being multiplied by things that are themselves going to 0. And in some sense are going to 0 faster than the natural log. Okay, so all that being said, let's scroll down to the end. And let's finally do what I had mentioned earlier. Let's calculate h of 1/3, 1/3, where I'm now talking about this h, right? This one that only depends on x and y. Okay, if I do that, then what is it? It ends up being, I'll write a little bit of it. So it's minus x ln of x minus y ln of y minus, here was 1 minus x minus y, which also ended up being 1/3 when x and y are both 1/3. So minus 1/3 ln of this thing, which is 1/3. All right, so you see here that I have a sum of 3 over 3 ln of 1/3. So I just have negative ln of 1/3. And this is ln of 1 minus ln of 3, which is just ln of 3. Remember that ln of 1 is 0. Okay, so I finally get the ln of third that I've been looking for. And that is, again, the h value at x equals this, y equals this, and z equals this. So we now know the value at the only critical point in the domain. We also have argued that the function tends to 0 as you reach the boundary of the domain. So this is the reason that employing this argument is useful, because we didn't have to calculate any second derivatives and use the second derivative test. We can now comfortably say that this x value, y value, z value, and this output value is an absolute maximum. So now I want to show you this last part here as I'm checking things off, the graph. So let's talk about the graph of the function. So I have plotted here, not that one, let me switch over to this one. There is the function. So I'm going to turn on my little scroller here. And I'm just going to pan around. You can see that, again, the function is, if we look at it in an XY view from the positive Z axis, you can see here the exact domain that we have drawn, the triangular domain. This is a line 1 minus x. This is the x-axis. This is the y-axis. And indeed, there's no portion of the function outside anywhere else, just in there. And you also see, if we kind of pan around back to the regular view, you can see that, you know, the applet is doing the best that it can to evaluate these very tricky products. But you can see that the function is going down to z equals 0. And it's not going to go any further down than that. But there are places where the function seems to have a large z value, relative to its other numerical values. And so there does seem to be a global and absolute extremum on this domain. And if I turn on the point on the left here, 1/3, 1/3, ln of 1/3, that is the point we just calculated. This is the x value, 1/3, y value, 1/3, and then we're plotting h of x comma y, not h of x comma y comma z. So the z value here is the output, which is ln of 1/3. And you can see that is indeed the absolute extremum. Okay, great. So we have solved one example. It took us a very long time. And this is what will happen with optimization problems. So we are going to go back then and scroll down to solve the second example.